Hi everyone. Today in the series of theory of computation lectures, we'll see what is finite automata. Okay. So we'll see what is finite automata and its categories. What are all the categories of finite automata? Okay. The first one is finite automata. So we divide this into two categories. So finite automata with output and finite automata without output. Okay. So with output in the sense finite automata will give, when you are giving some input on that finite automata, it will give some output. Okay, that category is that is one category. So another category is finite automata without output, which means you will give the input but it will not give any output. The automata will not give any output, but then by using the finite automata you will come to some conclusion. Okay, so that category is second category. Then in this first category you have two different machines, that is Moore machine and Mealy machine. This is not the part of our syllabus, but here finite automata without output we have DFA, NFA, epsilon NFA. Okay, these are all the three things we are going to discuss in depth in our theory of computation. So what is mean by DFA? DFA means the expansion is deterministic finite automata. NFA means non-deterministic finite automata. This is epsilon NFA. Epsilon in NFA we also have another classification, that is epsilon NFA, epsilon non-deterministic finite automata. Okay, now we'll first of all we'll define what is finite automata. Okay, see, before that we call this finite automata as finite state machine, finite state system. Okay, it is a design tool for, this is the application, this is the design tool for text editor and lexical analyzer. Okay, lexical analyzer. Okay, this is the one point we have to note down. Before, whenever we study some mathematical concepts, we should know the application of that particular topic, right? So in that way, finite automata is the mathematical model, simplest mathematical model of a machine. But what is the application of this finite automata is that it is a system, it is a design tool for text editors. So whatever you are using in the system nowadays, you have desktop or laptop or even you have mobile, right? So we have the text editor, right? So that is the application of finite state machine. So finite state system is a design tool for text editor and lexical analyzer. This lexical analyzer is the part of the compiler. Okay, you know what is compiler, right? So compiler is a software by which you convert the high level code into high level language into machine understandable format, right? So it is lexical analyzer is the part of that compiler. Okay, so this analyzer will scan the input whichever we are giving one by one, each and every character. It's just a scan for the character and it will separate the tokens, right? These things will be discussed in the compiler session, principles of compiler design. And just to know that the finite state machine is the application of, it is a design tool for text editors whichever we have in the desktop nowadays. Okay, so finite automata is the, now we'll define what is the definition of finite automata. So as I said earlier, it is a mathematical concept, so mathematical notation representation, right? So finite automata is the collection of 5 tuples. Okay, you just note down what are all the 5 tuples. So first one is the capital Q, second one is sigma, and then delta transition function, Q naught, and then capital F. These are all the 5 tuple notation of the finite automata. Okay, simply if they are asking for what is finite automata, it consists of 5 tuples. The first one is capital Q. Capital Q denotes finite set of states. Okay, the machine will have the mathematical notation will have some states, set of states. These states are finite number. Okay, just note down that finite number of states which is non-empty. Okay, so always whenever you define a finite automata, there should be some states, right? That should not be empty set. Okay, so now this is Q. Q is the finite set of states. Next tuple is the sigma. Okay, sigma. We already discussed what is sigma in the previous lecture. So it was like, it is an input alphabet set, right? The same thing here. So sigma is the input set. So these inputs will be given to the states, right? So machine, right? So machine consists of states, right? So you'll be giving the elements from the input set sigma. Okay, this is second tuple. Third tuple is the q naught, small q naught. So q naught is the initial state, or you can say it is starting state, otherwise you can say start state. Okay, so this is, it is, just note down that q naught belongs to capital Q. So as I already said, finite state machine consists of number of states. So now I am defining what is q naught. Q naught is the starting state of the set capital Q. So which means that we can denote that small q naught belongs to capital Q. So capital Q is the finite number of states. Q naught is one of the member in the set capital Q. Okay, this is what the meaning. So q naught belongs to capital Q. So and then capital F is the set of final state. So whenever you have start state, you'll also have final state. Okay, otherwise you can say it is acceptance state. Okay, so now set of final state is the capital F. The last notation is delta. So delta is the transition function, or otherwise you can say this is a mapping function. This is a mapping function. So just to note down what is mapping function. Mapping function, the mathematical notation is that for the transition function, you should take some state from the set capital Q, and then you should take some element from this input set sigma. Okay, when you take these two things, it will give the output as capital Q. Again, the meaning is that upon seeing input on particular state, it moves to another state. This is what the representation means. So we'll discuss with one example here. So example is that we have the transition, we have the machine, finite state machine here. So just to take this as an example, so these state, now we'll define what are all the members of this finite automata. So we also, as I said earlier, we have 5 tuples, right? So first one is capital Q. So for this diagram, what are all the capital Q? What are all the capital Q? I am asking the set capital Q. What are all the members of capital Q? So you know what is capital Q? Capital Q is the finite set of states, right? So you just look into the diagram and say what are all the states are present here. So we have 3 states, right? A, B and C. So this is the set, right? A, B and C. Other than that, we are not having any states. This is the set capital Q, and then we define what is sigma. So what is sigma here? So you have what you have A, B as the input symbol. Okay, set, the sigma set consists of 2 elements, that are, those are A and B. Okay, other than that we are not having any input, and then we define what is q naught. So now q naught is the starting state, right? Here in this diagram, what is the starting state? So I already said, like, whenever you see arrow mark coming from any state, it should not come from any state. The arrow mark denotes this is the starting state, right? So when you see B, the arrow mark, this is the incoming edge, outgoing edge of A, right? But here you cannot have any state, so we can call this as a starting state, start state. So q naught is the capital A here. Okay, and then capital F. What is the element capital F? Capital F is the facet of final state, right? But here I already said, whenever you double circle the state, which means it is a final state. So now final state is a set which consists of only B. So only B is the final state here, all other are intermediate states, we can say. So now we have to define what is sigma, right? So I already said what is sigma. Sigma is the capital Q cross delta is the capital Q cross sigma tends to capital Q. This is the definition, right? So now you just take what are all the states in the capital Q. You have 3 states, right? That is A, B, C, right? 3 states. You should combine with what? Sigma. Sigma consists of 2 elements, right? 2 elements. So I can have A comma A, right? One option, and then I should know upon seeing small a on capital A, where it goes, I should find out that. Okay, so it is again goes to some other state, right? That is was the representation. So now capital A comma small b, right? I should know what is the outgoing edge, right? When upon seeing b on state capital A, where it goes, that should be defined here. And then b comma a, what is b comma a and what is b comma small b, and c comma a, c comma b. Okay, this is one function, right? And then you are having q. What is q here? We have a, b, c, right? Three states are here, right? Now you just see one by one. Upon seeing these diagram, you have to connect these two functions, right? So now upon seeing small a on capital A, the state A, where it goes to B, right? So you just have a arrow mark from A, this to this, right? Just connect it. And then capital A comma B, upon seeing small b on capital A, where it goes to C, right? Just to connect these two. Okay, and then upon seeing small a on the state capital B, it goes to where it goes to A comma B, right? Self loop, right? It goes itself, it is like a self loop. So I can have it B comma A to A. Okay, it's just connecting to B. Again B comma B. So upon seeing small b on capital B, it goes to B, right? And then C comma A. What is C comma A? It goes to same state C comma B. It again goes to same state, right? So this is the mapping function. This is called, otherwise it is called transition function. Okay, so you have 5 tuples here. Those are capital Q, sigma, Q naught, capital F, and then transition function. So here two things you have to remind it. Q naught is the member of capital Q. Again capital F is the member of capital Q. Okay, so that is initial state is the member of capital Q, and final state is also the member of capital Q. And then delta is the defined as like a mapping function, so which is denoted by capital delta, which is represented like capital Q cross sigma tends to capital Q, which means this is one state. You should take one element from the set capital Q and one element from the input alphabet sigma, and you have to look for the move, right, where it goes. Upon seeing this input symbol on this state, which state the movement is there. So like this you have to see the diagram and then you have to answer it. So this is what the finite automata. So as I said, it has 3 different categories. One is DFA and second is NFA. Empty, that is epsilon NFA. Okay, we'll see what is DFA now. Okay, we'll see what is DFA now. See what is DFA now. DFA is the deterministic finite automata, right? So you know what is the meaning of deterministic, right? So you just have the meaning of deterministic. So we know we are going to define what is DFA. It is deterministic finite automata. Okay, this is what DFA. Okay, so I'm just going to define what is DFA now. So deterministic means you are very well know about the move. This is what DFA. So I'll define you now. If there exists a path for a certain specific input, okay, if there exists only one path for a specific input from the particular state. So note down the term only one path. There should be only one path for one input symbol. Okay, so I am just giving the example now. Just to take this diagram. So this has, so we'll make it as S0. This is starting state S0, S1 and S2. We have 3 states. So if there exists only one path for the input symbol, So upon seeing this diagram, you know what is the input symbol. Here you have A comma B are the input symbols, sigma. Okay, capital Q means you have S0, S1, S2. Okay, this is one set. Now you just I'm just defining what is DFA, right? So you just take a symbol, input symbol, input set A. First I am just considering small a. Okay, consider A and look for the diagram. So for the input symbol small a, I have only one transition from particular state, specific state to another state. Okay, when I give small a on S naught, I have only one path, right? Only one outgoing path. Okay, this is what deterministic. Okay, okay, if I see B, so upon giving small b on the state S0, it goes to S2. Okay, I'm very much sure about the path, right? I will not have a dilemma, right? Like I have to move this way or this way. You are very much determined about the path. Okay, this is what deterministic finite automata. So when I see small a on S0, I have only one path. When I see small b on S0, I have only one path. This is what DFA. So NFA. Now we'll see what is NFA. So non-deterministic. So which means you are not able to determine the path, right? So the definition is that if there exists more than one path for a specific input on particular state, that is called NFA, right? So I'm just taking the same example as S0, S1, S2. Okay, this is the diagram. So I'm just having A here, and B here, B. This is the diagram, right? So here you just make this as final state, this is final state, whatever it may be. This is the NFA. How we are saying this is NFA? We are checking the input. We have two input symbol here, that is A comma B. A comma B. I'm just look for small a. I'm just looking for small a. So upon seeing after giving small a on the S0 state, I have two transitions here. Okay, so by being on S0 state, you are looking for an input small a and you have two different paths. Okay, that is more than one path. Okay, so S0 comma a goes to S1 as well as S2, right? So you have two different paths. This is called non-deterministic finite automata. Okay, non-deterministic finite automata, but here you only have only one path. Okay, I hope you understood what is finite automata, what is NFA, what is DFA, what is the phi tuple notation. These are all the very basic terms in the upcoming lectures. If you have any doubts, please comment on the comment box. Okay, thank you. We'll see remaining in the next lecture.